This is our class for Introduction to Edge Computing. This is a follow-up of one of the fundamental course also, no, yung cloud computing. No? So it's natural progression, and you'll see why in a bit. So for the class of edge computing, no, of course, we're going to be discussing edge computing, history niya, and then key components, and then current challenges and limitations. What we're trying to solve, what it cannot solve, what's the inherent issues. And then since it's closely related to cloud, no, and the similarities niya with the cloud, and of course, differences. No? So we could delineate what is cloud computing, what is edge computing. And to cap it, no, it's a key learning points discussion. And this is a fundamental course, and it's actually one of the shorter courses, no, for IORA. Then of course a list of references. So as with cloud, we got this question, no? What really is edge computing? And the short definition is, well, it's a distributed computing paradigm, no? Where edge computing makes processing and storage of data instantaneous, no, by bringing computing systems and some storage, no, as close as possible to the device, application, or component that collects or generates data. So as close as possible, it could also mean within the device itself. So advantages, it's better control, no, over data. You reduce cost on some part of the infrastructure, but of course, you need to increase cost dun sa edge computing, no, on the actual device itself. You also are able not to provide faster insights and actions, and you could enable streamlined operations. We'll see in a bit. So here is an example of edge computing system from Spiceworks, where you could see that a lot of edge computing use case, no, pertains to vehicular networks or IoTs. No? And most of these edge devices, no, they produce data, and they need decision points, no, one way or the other. Let's say for industrial control system, no, let's say you have a pipe, no, with a certain number of pressure lang, and then at some point you're breaching that pressure, no, there would be devices, no, within that system, no, that would sense it and would have to decide, no, if they're gonna open up a release valve or they're gonna continue operating until a threshold gets breached. Now, while in theory, no, you could have that sensor send that data to a central cloud infrastructure, no, and have that cloud collect all this information and then decide, no, whether to open the valve. On some real-time decision-making points, no, that might take quite a bit, no. I mean, it might be in the milliseconds, no, but that would still be an issue, no, on real-time systems. No? So you would want that sensor to also be able to decide, no, based on what it was programmed to do, to either open the valve or continue operating until a threshold is reached within itself, and just report that action, no, and data collection to the central platform. So again, or if ever, no, it's gonna be somewhere near that device, no, or within the facility. You don't want a facility in Batangas, no, sending data to the cloud in Europe, no, and then the Europe cloud would be able to decide whether to shut down or open the valve. There's a lot of things that would go wrong there. So it's either you would have that decision point within that device or IoT, or it's somewhere near, no, with the edge platform. So again, here's an example of that. Another example would be maybe vehicular networks. No? Could you imagine, no, your car sensing, no, that there's an impending collision, but it cannot decide on its own. It has to send that data back to the cloud, maybe somewhere in the US, okay, and then have that cloud, no, instruct your car again to start hitting the brakes. No? So a lot of could go wrong. It's wireless. There's latency, there could be interconnectivity problem, there could be telco problem, and environmental problem. So there's a lot of issues that could go wrong there. So you want the car to be able to decide on its own that, yeah, I'm sensing that I'm going too fast. There's an object that stopped somewhere there. And if I don't hit the brakes now at this pressure, no, I'm gonna reach that object and induce a collision. So you don't want that. So just some use cases for edge computing on why cloud might not be the best solution here. No? But if you could see the environment on the example edge computing deployment here, there's still data center cloud, no? But they're more for holistic view, no? Not really for processing real-time data. You got this edge computing platform, no? Which will discuss the key components, no, that would happen. So history, based on edge computing is based on content delivery networks, no, developed in the 1990s, no, to serve videos and others. No? And on 2000s and until now, no, this CDNs involved into hosting apps, no, on edge servers to develop, no, the earliest form of commercial, no, edge computing. What's happening here is like this one from graph from Hostinger. You would want to typically get your data as nearer as possible, and that's what the CDN is trying to solve. In the olden days, where a software company would want to release a patch, and let's say they're a US-based company, and they're gonna host the patch. Everyone in the world would want to connect and get that patch. Chances are they would be overwhelmed with the request. So that's not theoretically uh, physically, yeah, in itself, no? They cannot serve all these clients at the same time. We still have that issue now, no? Let's say Microsoft or Apple released a patch. Typically, they have a central location or the source or the origin server. Nowadays, they are using CDN. They would see this patch or updates to various CDNs. Okay, and when the time comes that to turn on, that everyone could download the updates, the user would try to request on cache servers, and try to check. I'm Microsoft client. I have a Windows 11 box. Do I have an update from the edge server? And at that point, the edge server should have preceded files and patches on it. So now that the user will not need to go to the origin server, and have all the rest of the world Windows 11 operating system to go to the origin server and overwhelm it. Everyone now is distributed to the nearest edge server, which solves two things. No? Now, the origin server will not get flooded, and the user experience is much faster, no? Because of latency issues. No? The edge server is nearer to the user, latency is lower, and it's able to get the data in a short amount of time, no? As compared to connecting directly to the edge server, to the origin server. So that's how CDN works, and in theory, that's how edge computing works. And we got this cool comic strip, where in the 70s, we actually have central computing, or might call it an initial cloud platform, where you have a central mainframe, and then you have a lot of terminals that access it via timeshare. It come 80s and 90s. Microsoft and IBM had this concept of computer in every home. And it did come true around mid-2000s and 2010s. Most of us would have their own computer at home. And they had the issue of, okay, we're running individual apps. We need to centralize it more. Hence, while the virtualization technology was designed in the 70s, it was reborn as cloud computing. And now everyone is running some sort of a dumb terminal, so to speak, not as dumb as the 70s terminal. You could still run browsers, applications, and heavy heavy duty or heavy processing systems now on your workstation, but typically you would upload this data to the cloud. Now, hence the second uh, s- second part of the comic strip, no? But sometime later, no, they realized that, well, centralizing to the cloud, no, had a few issues on its own. One is bandwidth, another is latency, and of course, if it's near real time or real time, no, it's not possible to use the cloud. Hence, the iteration now is, well, here you go, you need a brand new edge server near your location. So that's how uh, this comic strips actually presenting, no, how we came to be to edge computing. So edge computing, no, we are trying to solve, no, and have these data generating endpoints send this data, no, to a centralized platform, either via LAN or WAN, maybe both. And this centralized platform branches the data and sends the output back to the endpoint. As you've seen with the basic use case a while ago, no, with a control system or a car that is connected, there are issues with more and more devices, no, being connected, no, even with few devices, no. Too, you got some of these issues, no. For more devices, you have scalability. You've seen this happen, no? If there's let's say a news that breaks out that there's an exam that's the results gonna be released, but everyone in the Philippines tries to access that server and the server goes down. Hence scalability and volume. Another problem with cloud is latency. Especially in the Philippines, most major cloud computing platforms do not have a location here or a data center in the Philippines, since it has to be shipped out of the country. The data has to be shipped out of the country, likely through submarine cables, while it is still in the speed of light. No, there are still latency. I mean, you cannot beat physics. No, the moment data goes out of the submarine cable, typically you'll notice 30 or 40 millisecond at least, no, na additional latency for this connectivity. And if you're again operating items, no, or IoTs or systems that needs real-time decision, that 40 millisecond and then additional 40 millisecond for a round trip, no, might not cut it. No, you need decision fast. So again, these issues are highlighted if you have this just notion of deploying endpoints that generates data and then the cloud. Medyo maaga, no? Kulang sa kape. At
Hi,
continue.
Mon. Tony
Hi,
here.
ma'am. Anthony, guess what?
Ah, mas naintindihan ko na yata ngayon yung pinag-aralan ko several years ago.
Okay.
Ako dati, bakit yung mga train drivers and bus drivers sa Netherlands to, may binubuhat silang parang malaking storage. Parang malaki,
Mm.
ano ang tawag doon, yung mga disk natin na malalaki before. Tapos isasaksak nila doon sa machine and then iiwan na nila. So that is probably the edge computing that you're talking about.
Yeah, for data collection, telemetry ng bus. I've also seen that CCTVs for the buses, no? Kasi while we do have the infrastructure to send data 5G, no, there would be some areas na mababa yung signal, no? So they would want to store, no, all the stuff happening within the bus for regulatory and legal reasons, no, stored within the bus itself. So kung may nangyari, baka hindi pa uso yung SD card for dash cams. And typically for a bus in Europe, no, ang daming cameras yan, hindi lang yung harap, no, pati loob, pati gilid, pati likod, no. So there's a lot of camera feeds. And you don't want to send all that data out, no, to the cloud, no. Again, you have that issues lalo na kung let's say maraming bus. Sending it to a central server, no, to store those daytime images, no, pati yung telemetry ng bus, no, nag-i-speed ba, GPS coordinates. Again, you want to collect all this data for analytics, no, at some point. Maybe they would just batch processing it every week or every month. And then decision makers would identify, no? Itong routes ba na to, konti yung tao, dito mas maraming routes, so could we minimize yung yung trip on routes na konti yung tao and then put the bus additional bus, no, on areas na mas maraming tao at mas maraming nalilink. So that would be a key component. Nowadays, most likely SD card na yon, yung sinasabi ni Ma'am Tony na malalaking storage, no. Feeling ko ma'am, 1990 siguro. Hindi, joke lang.
Yes.
Ayun. But yeah, kasi malaki yung storage ng hard drive and nowadays mura, no? I mean per terabyte to per $2, it's still cheaper to buy hard drives, no? And then plug it. I think one of the drawbacks though would be power. But being a bus, no, as yung example ni Ma'am Tony, power would not be an issue kasi they have a huge engine to generate that to power those edge devices, no, within the vehicle itself. Okay, thank you for the input, Ma'am Tony.
Thank you rin mo.
So key components, no? So again, data flows from edge devices to the gateway. And from the gateway, no, they sometimes would process it if hindi pa na-process ng edge device, uh, collate it, and then send the edge data centers within a geographical location, and then likely, no, they still have a component, no, to centralize all of this processing, no? And then the data, no, is processed and analyzed at various stages, depending kung ano yung streamlining mo of operations. This helps reduce, no, latency, improve data privacy and security to a degree, no, and makes more efficient use of network bandwidth, no. So we'll see that in a bit, no, for when discussing these key components. So first, edge devices. So these are physical devices, no, or we could just think of it as IoTs, no, that has sensor, it produces data, it collects it, and processes it locally. And these devices could be anything. Again, smartphones, it's a good sample, no, for edge devices because, well, it has a sensor, no, a lot of sensor for that matter. Could easily put in microphone, no, for the calls. You got multiple cameras. You got gyroscope. You got light sensor. A lot more, no. And connectivity too. It has a lot of connectivity from GPS, Bluetooth, NFC, Wi-Fi, multiple standards of Wi-Fi, GSM, 3G, 4G, 5G, and even GPS, no, multiple forms of GPS. So a lot of connectivity for the phones, no. And our typical smartphone now, no, it's actually it has more computing power, no, than the desktops we had 10 years ago. So imagine the amount of processing power and storage, no, that we have on those devices. It's not uncommon to see a 1 terabyte smartphone, no, with storage, but imagine your computing power 2010s, no, where you have maybe 200, 300 gig, no, that's actually a big amount of storage at that time. Now you have 1 tera on a smartphone. And so these devices generates this data, no, like in smartphone, no, I take a picture, it's usually stored, no, within the device itself, but it has some components for processing. It's technically an edge device. Typical smartphone operating system nowadays, no, would do a lot of pre-processing on the picture, no, like doing multiple shots with multiple exposures and then combining them, no, to get the best clarity picture. Some of them would have some machine learning processing, no, again to sharpen the images, get the best out of this different exposures. They would also do OCRs, optical character recognition, no? I mean, I'm not sure if you've tried, no? If you search on photo libraries on modern phones, but you could search text, no? And the phone would search the text based on within the picture. And that is part of the pre-processing before it's being stored. Another is objects, no? They have machine vision being run on these images. So if you see, say, on our search, no, bridges, no, the device would have pre-processed this picture. They have this a lot of attributes attached to it, and they would show you, pictures with bridges, or specific individuals. Now they have facial recognition too. If I want to see a picture of my son or my daughter, no, I'll input the name, and it's gonna pre-filter all of those to you, no. So it's just gonna show pictures for that. So in case you haven't tried that, uh, check it out. No, it's actually very awesome and very scary too. They could do that kind of pre-processing and storing it on this equipment. No? Again, smartphones and modern IoTs, no, they have built-in processing capabilities for them to enable this um, analytics. No? And then they would be passing this to the next stage. No? Like, let's say on phones, we typically have cloud storage, no, for these pictures. So not really an edge itself, no, but you send this data directly to the cloud if you configure the device as such. But this cloud setup, no, for photo storage, no, they are using edge computing. They would have receiving edge servers near where you are. Typically, they would contact an ISP or a telco, no, so that your photos, no, would be sent, no, instead of directly to the central cloud photo sharing service, no. They would be cached on the telcos first, no, and then after a few minutes, or depends on the resource, no, they would be sent, no, to the central location for everyone, at least in your account, to see, especially if you do, let's say, a type of photo sharing with family. So any photos, let's say you have that set up in your family, any photos taken get centralized to a central photo album. So be careful though what you take a picture of. Everyone would be able to see it within your group. So to a degree, no, this helps reduce the amount of data transmitted, and to a degree, no, minimize latency. So that's how edge devices work. And again, factor in with the example na we did a while ago, no, with control systems and autonomous vehicles, no, or even just sensing vehicles, no, they need those data processed on site, no, and maybe probably, no, decide on site itself, and then just send the decision or telemetry after the fact to a central location. So you got these edge devices, and then you have the edge gateways. No? So edge gateways, they typically are middleware, intermediary devices between edge and the cloud infrastructure. No? So they would be nearer edge devices. Some of these edge devices might not have processing capability, so they would send all this data to the edge gateways. And the edge gateways would store, well, temporarily for some of them, and process this data, no, and send only relevant and valuable data to the upper layers or eventually the cloud. Why edge gateways? Typically, edge devices might be connected, no, via wireless, might have been, no, on the battery operated, no, which is very scarce, no, the which power scarce for the edge devices. But typical edge gateway wouldn't have that problem. It's gonna be wired in a small data center with cooling, with a lot of storage. No? So edge devices that has some limitation might, no, outsource the processing to the edge gateways. And the edge gateways would do all of this again, pre-processing, streamlining of analytics, and then sending it to uh, the next step, no, which is the edge data center. Typically, this is geo located, no, where near the edge gateways and the edge devices. Smaller scale, again, you have more resiliency here compared to edge gateways. Typically, edge gateways would be located in a campus or a building within reach, no, of the IoTs. Edge data center might be within a country, no, or a city, for that matter. Again, each and every step you are basically centralizing and processing data. And eventually, all of this at some point would need to reach a centralized infrastructure. And typically, this would now be hosted in the cloud. But at this point, no, this is not handling data and tasks that are time sensitive. No? You are processing real-time data in the edge gateways, no? Or if the edge gateway cannot do it, maybe in the data center that is close to the edge gateways. So that's typically the progression of cloud computing. So let me give you an example. So let's go with Ma'am Tony's example. You have CCTVs in the bus, no, with multiple cameras. Uh, let's think of a scenario where we would need a camera. At the minimum, no, you'll have a front-facing camera for the bus. You have an internal-facing camera for the passenger. Then you have a rear-facing camera for whatever happening at the back view of the car. So they want it again recorded for legal purposes. But that's the basic, no? I've seen buses that has a camera dedicated for the driver, additional camera dedicated for the gangway, and the entrances, no, of the buses. Then you have cameras, no, on the view for the left side and the right side of the bus, backward, back facing, and then front facing. So that's almost, no, at least 10 cameras for that alone, no? And imagine recording all of this camera in at least 1080p, no? The amount of bandwidth you need to store 10 cameras, let's say, just top of my head, 1080p might need 5 Mbps of traffic per camera. So that is in its own, no, at 10 cameras you need uh, that's not an exact bandwidth requirement. So you might be googling it and say, oh, di naman pala 5 Mbps naman. Yeah, just let's do a simple math, no? 5 Mbps per camera, 50 Mbps content. Shifting all of those data to a cloud solution, no? Maybe a wireless cloud solution. You might not have 50 Mbps in the bus's route, no? Some might be good connectivity. Some might encounter spotty connectivity, no? And that's just one bus. Imagine if you're in a city operating, let's say, 1,000 buses. So for 50 Mbps per bus times 1,000 bus, you need 50 gigabit just to store that camera. That's gonna be your minimum bandwidth for the data center. So that's a lot of processing. That's a lot of bandwidth. That is expensive. And you might not need all of those data, no? Anyway. So the easiest solution is if I can afford a 50 gigabit bandwidth, no? That should be up all the time. Why not, no, store this data locally on a hard drive? And that hard drive most likely would have a compute resource on its own, and then process it there. And in case anything goes wrong, let's say there is a collision or an accident or an emergency button is pushed, all that telemetry data would now just be the data that would be sent out, no, to the central location. So even with the 1,000 bus, no, I don't think you need 100 Mbps link, no, to gather all those data. But no, specific what bus number, what location, what time did an incident occur, because that data is reported, and that's very easy to send that notification even if the connectivity for the bus is spotty. So example, and roll over to similar example, no? Let's say you have a CCTV in your building, no, and you have multiple buildings, no, you have a conglomerate that you need to watch over. You don't want all of these camera feeds. Well, technically you do want all these camera feeds live, no, to a central location, but the bandwidth and resource that would take, no, very expensive. So what if we put processing power on the camera and it's just gonna stream, no, a subset of feed from the camera if it detects movement or it detects a person, no? So easy, no? If you're a conglomerate, easy to have 10, 20,000 cameras, no, for multiple location. Now you are able to reduce the amount of data that is transferred to the central location and the alerts, no, for the central location, especially at night, no, if there nothing's really happening, no, except bigla may say there's a thief, no, that climbed the fence and that the camera detected it. That feed, no, would now the camera would sense it. It's gonna trigger an exception that oops, suddenly a person appeared on the fence where it shouldn't have. That stream would now be out of 10,000 cameras. No? That's the only stream that's gonna get alerted to the central location, and now you have a focused alert, no, for those people monitoring that CCTV. That okay, I am only being fed, no, on a 10 camera monitor out of these 10,000 cameras, no, alerts and movements, no, so they could focus. Imagine if you are a person operating and monitoring that a 10,000 camera system, maybe you could only manage 50 cameras per person. So that's a lot of manpower also required, to monitor those a lot of those camera. But if you're able to streamline, your process, that each and every individual would be able to monitor 10 cameras, no, but only cameras that had movements will be fed to you. And then it's gonna stay there for additional 5 minutes, no, to check if there's any other thing that's going on. That actually saves, no, bandwidth and manpower with a basic, no, edge computing deployment. And again, you are empowering IoTs and cameras, no, to do the processing on its own, and then just send alerts, no, after the fact. And for this camera, no, I mean, again, storage is cheap. You could put high capacity SD cards on them, so they would have a local copy of uh, the how you call this, the feed, no, for the duration, all the feeds, no, would still be stored on the camera, but only alerts is gonna be escalated to the central location. So again, that makes it more efficient. Now you do have a problem at that setup. Now, what if the thief actually stole the camera with the storage, no, or destroy it or fire the gun at it? No? Um, well, you hope and pray that the storage won't be affected. No, but in case it does, then you have the problem that you only have the alert part, no, the camera. You don't have the entire recording because it's in the device itself. So that's a part of uh, the scenario that you have to take when handling specific use cases for edge computing. Okay, so with that, no, setup, no, you have this edge analytics and applications that you design and check, no, what are the deployment type, where are we having problems that the edge computing platform might be able to help out, and you also decide, no, what kind of issues with that kind of setup, as in on device storage, no, what kind of issues that would arise, no, with that edge computing deployment. So again, we're running efficiently, but there are specific use cases where the camera or the device would get destroyed or stolen. Then we will not have that information anymore. But in the overall scheme of things, no, I think that is what I would say, that would still be an acceptable risk rather than processing 50 gigabits per second of data that's thrown to the data center. And that would also mean, no, you cannot have a downtime from the data center, because at some point, no, connectivity goes out, all this live feed, if it gets fed directly to the data center, it's not gonna exist anymore anyway. So now, if you deploy the storage on and processing on the cameras itself, you might be able to get away with short downtime, because cameras would be able to cache this data, no, and transmit it when connectivity is back. So you got that how do you call this, pros and cons that you have to decide on. So for challenges, no, again, even though you have computing power, you would still be limited, no, for the edge devices. Again, some of these IoTs would be running very low low horsepower processors, no? Because chances are they are using battery operated, or uh, they are very you call this conservative, no, on how they would use their batteries or power, no? Which would also factor in security, infrastructure, deployment costs, interoperability, network connectivity, and scalability. So we'll see this in detail, no? So for limited computing and power and storage, no? So edge devices, of course, it's not a server. Typically have low powered processors on it. Again, realizing that most of these IoTs, no, may would be operating on environment that doesn't have good power supply, power source. So chances are they would be operating on battery. So they would have to conserve, no, and maximize this battery, no, for the lifespan of the edge device. You would also, of course, limit, no, the complexity of tasks that you could perform, the amount of data they could store. In the example now where we are trying to do the pros and cons and itemize the trade-offs. Let's say some camera system might be able, no, to process a lot, as with the cell phone example, no? OCR, machine vision, object detection. But turning on all of those features might be okay for a smartphone, because well, smartphone has, again, good processing power, and you're charging it every night. That might not be good on camera system that just operates on batteries. Typically for this task, no, each and every feature that you turn on would have its corresponding trade-off with battery and processing requirement. Aside from that, no, the more processing you enable, no, the heat dissipation, you could also lower the lifespan of these devices. The longer it stays on a higher temperature. So again, you have storage, you have computing power, but it's not a workstation or an edge computing gateway type of computing power. You have minimal, you could put it that way. Security concerns, no? These devices and node, you introduce more devices and nodes in the network. And each of these, no, would be connected to your network, and it's gonna increase attack surface, no? So edge devices could be stolen, and if the configuration to connect to your wireless network is there, no, anyone with an electronics knowledge that could dump the config from your edge devices could maybe gain a password to your wireless network. So that is an issue, especially if you deploy it, let's say, for Pag-asa, let's say, no, you have a rain sensor network that's connecting via Wi-Fi. And you deploy this in the mountains, in the farmlands, no, with not much physical security. So if someone, no, grabs that IoTs and tries to read the config, they might be able to get to your wireless password, no, and use it, no, to onboard their own hacking devices and hack your internal network. So again, you might want to consider privacy and security when deploying these kinds of devices that does not have physical security. Problem: if you enable security and encryption on most of these devices, there will be a corresponding penalty on battery requirement, because the processing requirements of this edge computing devices would also increase, no? So you got additional heat, and with that additional power consumption and reduced lifespan of that device. So again, there's a lot of pros and cons that you need to consider. Infrastructure and deployment cost. And you buy edge devices, you would also be maintaining edge gateways and data centers. I think that would be a given. But now the problem that you would be encountering is managing and maintaining edge devices. especially on setups where like again, let's say on the range sensor network. On instances that a device goes out, no, you have to make a decision. Is it cheaper for me to send a technician on a remote site, um, and then have all the troubleshooting equipment and all the spare parts on it on the technician's backpack, and troubleshoot it in the middle of a desert, let's say, or in the middle of an ocean if it's an oil platform? Or is it just better to have the technician bring in a working device pre-configured, go to the site, take out the faulty device, and then plug a new device that's working, no? And then do an offline assessment on what happened, no? So there's no right and wrong answer. It depends on the sensor network or the edge devices. Yeah, create and replace might be an option, or yeah, it might be too expensive that you really need to have spare parts, no? On at some point, no, you'll have some data on which components are actually failing, and at what time would they fail, no? Depending on their lifespan, then you would already have a large amount of spare parts, no, for you to replace that devices, no, and make it work again. There's also the problem of interoperability and standardization, where right, let's say you're deploying a 10,000 camera device infrastructure. There's a huge chance that you might not be able to get one manufacturer of cameras because they cannot supply all these 10,000 camera needs, no? So you would most likely be dealing with different vendors. So are all these vendors interoperable? Are they all complying to a certain standards? And I had experience now with big vendors in the network world that says that they are compliant to a certain standards, but when you connect them to a different manufacturer, they will not talk to each other, no? They say they're compliant. Both of these vendors are compliant to a standard, but they have different developers. So the developers would have a different understanding of how to deploy and develop these standards. And there might be some intricacies where vendor A think it's working with the standard and interoperable, but they're only able to test it within their own platform, and it works. Vendor B has the same conclusion, no? But when you connect each other, no, again, the minor intricacies of their deployment, no, had issues where they are now not able to talk to each other, even though both are claiming that they are interoperable and standards compliant. You also would have network connectivity issues, no? So if you're in the city, you might have 5G connectivity. If you're in the province, maybe 3G or 4G. And I've seen deployments, not really in the edge computing world, where sensors on the city network would have 5G connectivity, not a problem. On provincial networks, no, where they have spotty data connectivity, they would fall back to SMS-based connectivity, no? So they would be sending telemetry via SMS, which was very reliable. And ultimately, that's the only data they need anyway. So they decide the network that way because of the limitations for network connectivity. But ultimately, they still got the data that they needed. Also, scalability, no? Again, most of these edge devices, you would need to really think, no? What type of data are they generating? What type of data that I need to collect in a central location? No? This is gonna be different on each and every deployment. For some time, you might want to collect everything, of course, no? But again, the bandwidth, the latency, the volume, and the processing requirement might be a challenge, no? So you need to do a trade-off analysis, no, on what do you really need, what could be stored on the edge computing, what could be processed on the edge computing devices, and then what could be sent centrally. Then you have power consumptions. Again, some devices might not need all the features, no, but on some of your edge devices, you might need them. So you could, especially if it's battery operated, no, some device might have lower mAh for their batteries as compared to others. Again, for edge computing, especially for battery operated, and you want it to be efficient, no, you would need to compute, no, power consumptions and managements. Again, there are some processors and devices that are power consumption aware, and some of these IoTs, no, and edge devices would also be powered with renewable energy sources. So let's say a small solar panel that would be able to power them when there's sun and charge the battery, no? And then when the light's out, it's gonna be purely battery operated. And as we know, with battery, no, the environmental temperature also affects, no, the amount of power it could store. So we need to factor all of those, no, and provide the appropriate battery solution. And we also know that over time, no, the capacity diminishes, no, for batteries, no? So it depends on how long do we expect this device to live, no, within our project, no? We would need to mix and match basically power source and power storage. As with renewable, no, typically for renewable energy, storing power, let's say for a solar panel in a building or at home, no, it's very expensive. So you see a lot of solar panel deployment with just direct to power source, no? Very few would have batteries, and if they have batteries, it's just for basic consumption. They cannot possibly store because of cost and benefit trade-off. They would not want to store all of this energy, but they won't be able to use it anyway, no? And it's going to be very expensive to buy these batteries, no? So let's say for a typical solar panel deployment, they would apply to Meralco, no, for net metering, wherein in the morning, no, they would be generating energy from the sun, and typically morning consumptions in the Philippines are lower than night consumptions, no? So if they have spare capacity, they would sometimes store it in a battery if they have it, or if they have net metering, just feed it back to the grid. And of course, it's not 1:1 on how Meralco would purchase this energy from you, but you get credits, and you might be able to use that credits at nighttime. Now, when there's no sun, your solar panel is not generating energy, and now you have to take power from the grid. So that's how you would play with this current setup. And as mentioned, no, maintenance and management a while ago, no, if you have some issues on this device, you need to take into account. Do we troubleshoot and replace the parts, or do we just yank and replace the entire equipment, no? And do the troubleshooting in a central location. Okay? But you need strong internet, no, for you to be able to connect to your cloud without much of an issue. For security in edge computing, again, I would say you have physical devices. Your data is gonna get will be transmitting, no, from your edge device to the edge gateway to the cloud. So there's a lot of interception points there. And if you do not secure it properly, there could be privacy intrusions, no, where someone could be listening in or maybe injecting traffic that's not supposed to be there, no, and giving you false telemetry data. For cloud computing, typically this is a solved solution anyway. Um, with TLS and SSH and all these security protocols, now to connect and get data from your cloud environment and vice versa, no, to send data to cloud environment. I would say it's easier, no, for cloud to be defended, no, as compared to edge computing platforms. Okay. And with that, no, that's the last one. Again, this is a short course lang for edge computing. Key learning points. We've discussed how the edge computing is related to distributed computing paradigm, uh, how CDNs, no, were the initial edge computing before it evolves to what we have now. We got key key benefits, no? Like scalability, volume, reduced latency, no? For edge computing. We also have use cases, no? For uh, edge computing like accessible automation, streamlined analytics, flexible pricing models, and regulatory compliance.